So in video 1518, we made this. We put the ability of an exercise bike to charge a phone with an output port there. And if you thought that's all that video was about, then you're kind of right and you're kind of wrong. You're kind of right because actually it's quite an interesting application, and why don't manufacturers already do this? For a few pounds of extra bits and pieces, they'd be able to charge a premium price because you can charge your phone while you sweat a few pounds off. However, it is also an example and contains everything needed for any mechanical generator. What I mean by mechanical is that the power input is mechanical. In this case, right here, we stick our legs on there and pedal that. And that's our input. Our input here is our legs. Now, it doesn't matter what that input is. I could make that input my legs a windmill, a water wheel, a petrol engine if I wanted to make an emergency generator. It doesn't matter what it is. Whatever mechanical input I want to put into this particular machine goes right there. And in this case, of course, it's my legs. Now I could quite easily have bolted this thing on. Remember this? It's our turbo turbine made from spoons. If I'd bolted that on and pointed some water at it, it'd have done exactly the same job. Doesn't matter what I bolt on here. This is our mechanical input that we need an appropriate thing to capture the source of mechanical input, whatever that is. Doesn't matter if it's your arms, doesn't matter if it's your legs, doesn't matter if it's a windmill, doesn't matter if it's a turbine, whatever it is, it goes right there. After that, we've got this. This is a big pulley wheel and belt. And what it actually represents is a gearing system. Because here, I'm putting in mechanical power of some description. In my legs, I've got relatively high torque but slow speed, and this bit, which is the bit that generates electricity, works much better at high speed. So I need to turn that low speed into high speed, and for that, I use this. It's a gear section. It's exactly the same with a turbine. This turbine will turn a stupid rate of knots, but it's still not quite quick enough. Remember, we'll talk about this in a second, but remember, generation is a function of speed. The more speed we can get, the better. So we always have a gearing system in order to do that. And the gearing system can be one-to-one, where you do it as a direct output, or you can change that gears by changing the relationship of these pulleys. Now in this exercise bike, it does it automatically for us because they're already there. But component 1, mechanical input. Component 2, gearing system. And then we come to component 3, which is this bit here. This bit is the actual generation bit. It's the bit that interacts with the coil there and creates the electricity. Okay, what I've got here is a coil. It's a coil from a microwave oven turntable motor, and I've chosen this because there's lots of turns of very thin wire. That's important. In the centre there is a block of metal, and I've put it onto the meter with the pip reader so we can see what's happening, and what we can see happening is nothing at all. I've got a magnet here. If I move that magnet across that coil, we'll see it generate, and we'll see that with the voltage change. So watch that voltage. We can see the voltage going from plus to minus. It's creating an alternate current. And of course it's doing that because I'm moving the magnet. If I put the magnet on there, watch what happens. Nothing. Nothing at all. Because the magnetic field must move. Now if I do it only north, I get a tiny movement. If I do it north to south, I get a big movement, and I want a big movement because big movement generates more. Just having a north field on there won't do anything. That field must move. The field moves, the biggest range of movement it can get is going from north to south. Now it doesn't matter if it's always north, we'll still get an alternate current being generated because it builds the field and then collapses the field, and we get a back reaction. So it's always an alternate current irrespective of which side of the magnet you actually put on there. Now there's a whole lot of reasons you can go into that if you want and tie yourself in knots about why, but the simple fact is that field doesn't move, it won't generate. Why? Who cares? It won't generate if it doesn't move, and the biggest range of movement you can get is north to south, and the generation will always be AC within that coil. That's why these magnets here are north, south, because they get the biggest range of movement. If I put them all north, I'd get a small range of movement, but I would still get an AC generation. They generate because that field zips past that coil, and as it does that, there's a bit of iron in there, makes the field go down there, intersects the coil, and it does that directly in the relationship with the speed that that north-south field zips past that coil. So the amount of generation we can get out is related to the strength of the magnetic field, the speed at which that magnetic field changes, and the number of turns or length of wire that are influenced by that magnetic field. I put a single coil here. Now I chose this coil because there's lots of turns and it's very thin wire, and I know it's not going to generate much in the way of amps. So I chose a coil that has lots of turns so we can get a nice high voltage. But that coil and this coil are identical. This is just a lump of iron with a coil round it so that there's a magnetic pole here and here. It's exactly the same in a motor. This is just about 24 coils round around 24 little poles of magnets and joined up here so they come out and looks like one. But it's just 24 coils, exactly the same as this. This is just a neat package, and this is easy for me to handle and get because they're easy to get. But there's no difference functionally between what's going on in a standard stator from a generator or a motor and exactly what we've got here. We've just arranged it so that a magnetic field will zip past a coil. That's all that is, and there is no difference here than there is in a standard motor or indeed a standard generator. This is a DC permanent magnet generator, which is exactly what this is. In here we have that rotor, which is a bunch of magnets, and we have some coils arranged just like this. So this and this are the same thing. They're our generation section where we're taking the mechanical input, we've geared it to the right speed, we've got this which is turning very quickly, interacting with that coil, and that is generating us an AC output. So have a look at this. Want to guess how much it's generating? Well, it's generating nothing. It's generating nothing because I'm not turning it. If I turn it, now it'll start to generate because the power doesn't come from the coil. The power is actually here where I'm turning it. This transfers that energy into electrical energy. So if it's easy to turn and I'm not getting much electrical energy out of it, well, I did this as an example with one coil, and that's why. It's got nothing to do with that. It's got to do with how much I put here. If I want more electrical energy out of this, well, add more coils. You want more amps, then connect those coils up in parallel. You want more voltage, connect them up in series, and you'll get more out. But remember, every time you do that, you increase the torque requirement. Now, I'm able to produce a certain amount of torque with my arm. If I put too many coils around there, I just won't be able to turn it because the torque will be too much for me to be able to put in there with my arms or my legs, or equally with a windmill or a watermill, because the power is not here. The power is here, and I need to put enough power in here to turn this against the torque to generate. Having one coil just demonstrates it'll do it. If you want more, put more coils on. If it's too easy, add more coils. If it's too difficult, take some coils away. Now we could use that AC output directly, and we've done that quite often by lighting lights with it, that sort of thing. But it's much more common for people to want DC for things like charging a battery bank, for example, in solar and wind setups. So after it comes out of the coil in its AC waveform, we need to change it to DC for those kind of applications, and that's exactly what that does. That's a rectifier, and it's right there, changing the AC to DC. So once we've done our generation, we very often want DC, so I have to change it. We change it by using a rectifier right there. Now this is all over the place because of course we've got a changing field that's passing this at varying speed. Just remember, strength of field, speed, turns of wire, they really influence this. My legs are on here. It's going to be changing its speed. The wind is on here, it's going to be changing its speed. There's water on here, it's going to be changing its speed. Its speed will change, this will vary and fluctuate and give you a dirty output. It's all over the place. So one of the things we need to do is make sure that that's clean. Now we can do that by putting a capacitor right on here. If we put a large enough capacitor, we can clean up that output. If we want a nice clean output, a good stable output, then we need voltage regulation. If we use voltage regulation, we can change the voltage from the output voltage. Remember, the output voltage will change. We can regulate it, stabilizing it, using a little circuit that we just buy off the internet. That little circuit you can make yourself if you want to. or you can just bring a capacitor right here to do a reasonable job. But they're so cheap and so easy to buy, why not buy them and use them? But the function of this is voltage regulation and changing the level of the output voltage to the level of the voltage that you want. In this case, it's 12 volts. I've got a varying voltage coming in, maximum at 40 volts, I know that because I tested it. I want a stable 12 out, and that's what that does. That regulates the voltage and steps it down. So it goes from an irregular DC to a regular DC at the output voltage that this will generate, and then to the voltage that I want, which is the 12 volt voltage here. I take that voltage and take it to my output point, which is here. Now I wanted to charge a phone. So in order to charge a phone, I need further regularization, stabilization and voltage change, and that's exactly what that does. That is the bit that changes it to what I want it to be for the job that I want it to do. You don't necessarily need to do that. If you came straight from here and attached it to your battery controller, you'd have a battery charging unit. So this simple setup can be seen as a way of charging your phone from an exercise bike, if you want to see it that way. And equally, it can be seen as the answer to every single question I've ever been asked about wind turbines, water turbines, power generation, and storage. It's all right here. All we have to do to make this store into a battery is take those two wires, put them through our battery controller, and then add a battery to it. That would then store it to a battery. Here, all we have to do is change the mechanical input. Put a Pelton wheel on it, put a turbo turbine on it, get yourself a walking wheel. Here, all we've got here is a generator section. If you don't like this, bolt that onto it. It's all here. This is every single logical section to take a mechanical input and turn it into a usable output. And it's in blocks. Mechanical input, gearing, generation, output rectification, output control, application. All right here. Nothing else to it. So that is another way that I think is slightly more useful of seeing what we actually did in that video. Anyway, I hope the explanation helps. I hope it does in fact form a picture in your mind of what the logic is. It really doesn't matter what the individual application is, as long as it contains those components. And as a complete aside, incidentally, if I put magnets on here, I could equally have put a belt onto that. If I put a belt onto that, I could have driven anything at all. An alternator, a washing machine motor, this DC generator, anything, by taking a belt from here and connecting it to the pulley, which is what Luke's done. So it's all in here. All you have to do really is have a little bit of think about it and then see the logical blocks that have been demonstrated in this particular application. Anyway, I hope that helped. I hope you enjoyed the video. Thank you very much for watching, and please do remember to like and subscribe.